Okay, so let's look at a tank first. Oh my God, I can't draw that straight. See how much you remember from fluids. Oh, you changed it to yellow? Oh my God. Okay, so here we got M dot out. You want to call it, this is M dot in. This is our height H. We're going to make a control volume, which is this dotted line. We have a diameter of the jet or the exit, and then we have the tank diameter. Well, I'm showing you a few things. First, like anything you visualize, you can write your own mathematical equation for to solve for something. Okay, it doesn't matter. Velocity, speed, position. Here, the water's changing height, and it's a function of time. You can create an equation for that and look at that and plot it. Okay, this is going to help us when we get to optimization of the gearbox. And like, okay, how do you analyze machine design? You got gearbox stuff. Okay, and then we have to use some kinematic equations to solve for the train to get there. I think we wanted the shortest possible time to go 100 meters, and we'll do that later. Okay, but all of this is going to prepare you for it. Plus, I'm reviewing some fundamentals that you learned in other classes. Okay, so control volume. Control volumes are this dotted line. They represent a boundary that changes. Okay, so when we do thermodynamics, this room, if we close all the doors and we have an imaginary boundary in it, okay, all right, with the doors shut, nothing can go in and out of the boundary, then it's a closed system. Okay, here we have an open system because we have water leaving. Okay, now can you tell me fundamentally what is equation for conservation of mass or mass flow rate? Or think about your tub, right? You turn the water on, it fills up, right? And then it could empty in the drain. So you have so mass flow rate or volume flow rate? Almost. A times V is volume flow rate because the units are meters cubed per second, right? Okay. Mass flow rate is rho AV because it's density, area, velocity. Okay, cool. Now, what I was talking about is this fundamental equation. The change in mass of this control volume or the water in your tub over time is equal to the mass flow rate in minus out, right? That makes sense? If it was steady state, you know what steady state is? What steady state means? What? What is constant? Sort of. Okay, flow, everything, sure, yeah. So mass flow rate in is the same number, mass flow rate out is the same number, but the mass of the water doesn't change. That's the key. So whatever comes in must equal going out. Guess what? That's thermodynamics, conservation of energy, right? In and out, okay? Here, though, what's happening? It's actually the mass is the mass flow rate is actually like in. Well, I'm going to talk about that in a second, but like we're losing water, right? So it's not constant, it's not steady state. Okay. In this particular problem, we're going to assume that the mass flow rate in is relatively small compared to what's going out. So we're going to put that to 0. Makes life easy. Engineering assumption. Okay. So we're going to throw that to 0. Now, the mass of the tank is rho times VT. So what we're going to do now is we had our fundamental equation, conservation of mass. Each term in there, m and m dot, we're going to break down into equations. And you're going to see how we can find an equation for height as a function of time. Cool. All right, let's keep going. So the mass of the water in this tank is the density of the water times the volume, right? Does that make sense? Okay. We can break down the volume by what? Keep a little simpler. What's volume? There we go. Times the height. So if you know the area of the circle, because it's a tank, and you times by the height, it's volume, okay? You'll get it. You'll get it. Okay. And then the mass flow rate out, you told me was above. It's rho AV, but of the jet. Does that make sense? So we got the mass of the tank, we got the mass flow rate going out. We're going to plug those back in. I'll do those in green. So D of rho ATH over DT equals negative rho AJVJ. Let me make that clear. So we made a sketch. We labeled variables. We're using conservation of mass. Now, what I'm going to do is I'm going to take out rho AT, and we have DH DT equals negative rho AJ VJ. Anybody know like why we could take out rho and AT in the parenthesis? It's part of the derivative, but why can't we take it out? Do they ever tell you that, and you ever do anything like this at calculus? We're assuming it's constant. Okay. So the density of the water is constant. The area of the tank is constant. Okay. All right. Well, the densities cancel. And we now have this. So this means that the change in height, dH, over the change in time is equal to area ratio times the velocity. Okay. We're almost there. Because we don't know right now what? The velocity of the jet. But what fundamental equation can we use to get that approximation? Well, we already used mass flow rate and volume flow rate, so we can't use that. There's another fundamental person or equation that you've used in fluids. Starts with a B. Bernoulli's, right? Because that is so conservation of energy, right? We use conservation of mass, and we can use conservation of energy. Okay. So conservation of energy, but it's of a fluid, right? That's why you use Bernoulli's. So I'm going to draw the tank again. Here's the water. You remember what you have to do for Bernoulli's? Like on a sketch, what's important? Yep. Where do you want to do that? Right here? We'll label that 1. Right here, where it goes out. Okay. Why isn't the bottom one number 1 and the top one number 2? Because it what? Okay, in which way is the fluid moving? Yeah, so it's always the direction that the fluid's moving. That's how you go 1, 2. Okay. Now, what else what else is very important in Bernoulli's on the sketch? What's that called? Reference or datum? Yep. Okay. Yep. Yep. Because in this datum now, Z2 is 0. Okay, cool. All right. Now, assumptions. What can you assume? Yep. P1 equals P2, and that's atmospheric, right? The point 2 shoots out at atmospheric pressure too. What does that mean in terms of gauge pressure? Zero. Because it's your pressure minus atmospheric. So if your atmospheric pressure, the gauge pressure is 0. That makes it easy too, right? Okay, cool. All right, keep going. What else can we assume? These are all the assumptions for Bernoulli's. What about the temperature at 1 and 2? Yeah, they stay the same. Okay. Sure, yeah, steady flow. There's no work, mechanical work, right? Yep, and what does that mean in terms of temperature? I think I spelled that wrong. That means the temperature is the same. Otherwise, if you heat, friction, right? Yep. No mechanical work. That means there's no turbines or pumps, right? Frictionless. And we could say that Q is 0. And do you remember, Hank, because you had thermo, do you remember what that means in thermo? What's the fundamental word used when Q is 0? Adiabatic. It's adiabatic, meaning there's no heat loss. Okay. All right. What else do I have? These are just some things you just told me. Z2 is 0. Z1 is H. V2, we're going to call the jet velocity. And this last one, guess what the velocity at 1 is going to be? 0. Yeah, because it's a huge tank at the top. It's moving relatively slow than what's going out. Okay. If you put that in there, it'd be kind of tricky. You'd have to guess. It becomes a hard engineering problem, right? We're making an assumption now. All right. So now we've identified our assumptions. We made a sketch. And looking at these assumptions, we can use Bernoulli's, right? So do you remember that equation? Yep. Sure. Keep going. Yeah, I'm going to write it slightly different. Instead of your specific volume, I'm going to do density. Yep. That look familiar? Right? Didn't know you could do all this stuff with Bernoulli's and mass. Now, again, if you take thermo, this black equation, this equation I just wrote, is part of the big thermodynamic equation. Okay. Because thermodynamics, you look at pumps, turbines, heat transfer. There'd be other terms on each side. Okay. All right. Same with heat transfer. Okay. We'll go through that. We'll review thermo too, especially for those three that haven't taken it. It's good to know that equation. Okay. Hank, you remember that long equation? You could cancel a bunch of stuff. Okay. So what can we cancel here? We get a lot, right? This and that. This and that. Holy crap. What did we get? Look at that. It simplifies to that. Radical 2GH. You know, if you ever popped a hole in your pool, that would be pretty damn close to the velocity of the water spitting out. Be pretty close because there's not much losses to lose. Okay. So if you ever have a hole in your pool, figure out how to find that. But as long as you know the height, you can figure out what the velocity is going to be. Okay. So now, guess what? Now we can plug it back into that DH equation. Look at that lovely equation you just figured out. You should go home and do this in front of your friends or your family on a chalkboard right in front of them, right? They'll look at you, like, what are you doing? Say, I'm doing math. Or you just derived, but you didn't know using conservation of mass and Bernoulli's conservation of energy. Okay. There's actually 4 major kind of ways to create equations. FBDs, we did that with vibrations, right? Conservation of mass, conservation of energy. Okay. Those actually, there's only 3: forces, energy, and mass. Okay. You've heard of shock waves, right? Maybe I'm going to do that. I'm going to talk about shock waves in a converging, diverging nozzle. We'll derive, and we use forces, conservation of mass, and energy. And that's how you can get every equation on the fundamental of Earth, pretty much, or engineering-wise. Okay. So, boom. All right, what else? My last page. Okay. First off, what the hell is this? Yeah. Yep. Okay. Mathematically, what is it called? Well, we use conservation of energy and use conservation of mass to develop this differential equation, right? And what does a differential equation solve? One number? 2 numbers? It's a function, right? You're going to end up finding that h is this. And I'm just going to give it to you, but you can try it on your own. You actually just move delta t on the right and you integrate, right? Okay, let me just make sure you understand like limits just real quick. So technically, you would have this. We're not going to do this. I'm going to show you numerically how to solve it, okay? It's actually pretty cool. We're going to program. So we're going to have limits here, right? Oh my God, that was terrible. Let me do this. Before I continue here, that's a differential equation. You integrate both sides, and you can get this boxed equation here, okay? With limits. What the hell are limits? Remember what limits are? Yeah. So on the left, what does DH go from? Remember? Yeah, initial height to H. And then over here is initial time to final time. In this equation, do you see T naught anywhere? Because we're going to assume it's 0. But I did have H naught, right? Because we have to know that. Okay. So again, differential equations, this one is a very simple. It's first order. You can just integrate, which you've done before, okay, with limits. And you should have, now I don't know if it goes like this or if it's going to go like this. I don't know. Okay. But it's going to do something. Okay. I think it's the first one. Okay. That makes more sense. It's because it's to the second power. Okay. But again, differential equations, first order, integrate. You now have a function for H. Okay. Now what we're going to do is we're going to take this equation And we're going to program that in MATLAB. And we're going to solve for H. Okay? So, questions, comments? So let's program this now. Let me just copy this header. All right, let me paste that. Okay. So this is, I'm just going to put the title here. So time to empty tank. I'm going to save it like that, okay? And this will be homework 2. So just save it, whatever, homework 2, time to empty. And then you can fill in that other stuff later. All right, let's do givens. Can't spell. DJ, 3 divided by 100. And we'll do meters. DT is 8 meters. G is 9.81. All right, tell me, can you tell me what these two are? Like, go ahead and try them in MATLAB. Remember the area of the tank? Is it pi d squared over 4? You can write pi dj squared times 0.25. Meter squared, same thing, pi dt squared times 0.25 meter squared. Okay, I'm going to put some of these in. We'll talk about it. Yep. Yep. Diameter of the jet. Yep. Yep. So when you ever heard of the numerical methods, okay, basically it means that we're going to predict what's going to happen in a numerical way. So you have theoretical, which is that equation, okay, that you actually solve and get an equation for. Numerical, meaning you start with a value and you march forward and you get a number, then you plot that, okay, or there's experimental, okay. So usually we try to match experimental with one of the two, okay. Sometimes you have 3 models, theoretical, numerical, and experimental, and you see which one lines up, okay. Now, what we're going to do is we're looking at this equation. We need to solve this numerically, meaning we're going to start with an H value and we're going to work our way until a certain amount of time. Okay. Now, I'm going to show you. I got to go so I can see here. Where did that paper go? Okay. I'm going to go back to here and just show you something. So, DH. That could also be written like this, right? And that means it's H2 minus H1. So a second height minus a first height. Or H3 minus H2, H4 minus H3, so forth, right? Does that make sense? Okay. So if we write this out as delta H equals, and can I call this stuff right-hand side? Actually, no, I don't want to do that yet. Okay. Negative AJ over AT radical 2GH times delta T. So H2 minus H1 negative AJ over AT times radical 2G H1 times delta T. What did I do there? Let me zoom right in. Yeah, I wrote out the equation. And what we're going to do is, in order to find H2, you're going to add the initial value, H1, plus that side, which we'll call right-hand side. Does that make sense? I think all of this is times delta T. Oh, crap. Undo. There. So what we're going to do is, on the right-hand side, we're going to use the current value, H1, which is 3 meters. We're going to find what that number is, and we're going to multiply by a time step, delta T. We're going to pick that. Then we're going to add that to 3 meters. But in this case, it's a negative in front, right? That's why it goes smaller. Okay? And then how would you find H3? Well, so you could, so like H3 minus H2 is negative AJ over AT radical 2G H2 all times delta T. So you use the previous H2 value, do the math, and then add it or subtract, okay? This is a pattern. When you see a pattern, what's that in programming? Yep, a for loop. Okay, that's why I'm showing you this. Okay, so we're going to do a for loop. Okay, so go back to MATLAB. How long are we going to do it? Well, I'll show you. I equals big T over delta T. And let's make this easy. So say it was 10 seconds. Or even 1 second. What is 1 second? What's 1 divided by 0.1? 10 or 11 seconds. And so it's going to do it 10 or 11 times, right? Okay. Now, the cool thing is you could just keep changing this, and the for loop keeps going more larger and larger, right? Okay. Or if you change this to 0, okay, and you're going to see something here in a minute, like the smaller your time step, the longer it's going to take to run the code. Okay. Because you got a lot more data points. So in here, though, guess what? It's going to be h of I plus 1, which is h2, equals the negative aj divided by at times sqrt of 2 times g times h of I. And that's all times delta t plus h of I. Now, you just have to remember how, when you write subscripts on paper, how that's converted to MATLAB for parentheses, right? Now, if you're programming in Arduino, if you're programming in Python, this format's a little different, right? But the way that MATLAB does it, it's I plus 1, meaning it's like 2 if I is 1. Parenthesis I means 1 and 1. So this is just like we just wrote the equation below. Okay. Now, we also need to do time, because we're incrementing that. So we're going to take our initial time and we're going to add delta t to it. And then we can plot now. Figure 1, plot time divided by 3600. I'm just going to get it into hours, and then h. And let's make it black with a line width 2. X label is time. This is hours. Y label is height, meters, and we don't worry about the title right now. We can do that. So once you get this, run it. Let's make sure it works and talk about it. Now you may have to change this, do like 1,000 or something, and go back to 0.1. I didn't copy this right. It's I equal to 1 colon T over delta T. Because you're starting with the number 1 and you're going by ones up to 1,000. What it was doing is it defined I as T over delta T, which is 1,000. We haven't defined H of 1,000 yet. Does that make sense? So 2.88, yeah, you may have to change. I think it was like 700,000. That'd be a while loop. Yep, I think that was too much. So 70,000 might work. Yeah, look at that sexy graph. I put 70,000, I think, in there. Yeah, it goes too much. But then you can, this is hours. It's like 12 hours, 13 hours. This is a small hole. But what I'm showing you is as you are getting this programmed and you're running the code and you see this horizontal line, think to yourself, well, does that really make sense? But look at the y-axis. Increase the time, okay? Now, if you bump your delta T up to like, try 5 seconds. And it still works, okay? But there are going to be some differential equations that you solve that if you go too high, it's going to mess it up, okay? Like I think if you do 50, does 50 work? Yeah, 50. It's a pretty like you can even do 1 second because it's so big. All right, now let's talk about terminal velocity, okay? Terminal velocity. All right, let's see. We've done a few things now. This is going to be forces, okay? We're going to have a tennis ball. So, and again, this can be applied, this type of analysis or derivation I'm doing can be applied to something that you're working on at your engineering firm or something, and you want to know more details about it, or you want to create a graph. Where do you start? Well, a sketch, right? And label, you could either label conservation of mass, conservation of energy, or forces. Those are going to be your fundamental stuff, right? And here we're going to do forces. So can you tell me if a tennis ball is in the air, what type of forces we have acting on it? Gravity. And I think I called this FW. Sure. So that wouldn't be a force, but we could put that it's falling down at V. Okay, so you got to be careful. So you can label things, just make sure, okay, we're dealing with forces or kinematics, which is acceleration, right? In velocity. Okay, drag. Which way does the drag go? Up. And I called this FD. So drag always opposes motion. Okay. So this is falling. Falling, yep. Nope, sorry. Yep, so say we're basically, you could do this experiment. I think I might have done this when I taught Area 320 experimentation and measurements. They went out to the top of the roof and they had an iPad and they recorded it. and it reached terminal velocity. And there's a cool app where you can actually put dots on and measure it. It'll tell you what the speed is. I use that for my parents have a zip line, put my kids on it, and I recorded it, and I calculated their speed as they went down. So anyways, yeah, so we're dropping the ball, okay? So yeah, drag. Yeah, there's actually a couple other ones, but we're going to ignore them. What happens if this ball was in a liquid? Like a beach ball, when you push down in water, why is it so hard? Buoyancy, okay? There is a buoyancy force in air. We'll write that so you know, okay? And the other force that I'm not even going to put on here is if this tennis ball is circulating, creates lift, but we're gonna assume this is a knuckleball, okay? Or it's not spinning at all, okay? It changes when it spins. It changes something else I'll talk about here in a second, okay? So if we sum the forces in the y, right, we can create a equation that will tell us how we can find it. What other assumptions are we assuming here? It's 1D, right? It's falling straight down. There's no wind. Actually, you could put wind in here, but if the wind, we want to make it go up, the drag force is a relative velocity between the two. Okay. But yeah, you could. Yep. So no wind, not spinning. It's falling straight down, 1D motion. So we don't have to do two directions. Okay. But you could. All right. Good. So we have how do I want to do this? Oh.
As fast as they can with it slowed down.
No, because there's an external force. You'd have to add that to the force term. Yep. Okay. That's why thrust. That's like thrust on a missile or something. Yeah. There's an external force applying that motion. Here, it's pretty much just gravity pulling down. Okay. So I'm just gonna. I think I did downward as upward as positive. It doesn't really matter because. So let me just write the equation. So we have drag FB minus FW equals M dV dt. Now the drag force is 1/2 rho V squared CD times A. You remember what the buoyancy force was from fluids? First fluids? No. It's the density of the fluid, which would be air, times gravity, times the volume submerged. But if it's a tennis ball submerged in air, it's just a total volume, right? So anybody want to guess what the density of air is? What's that? That is water. And the units would be 1,000 kilograms per meter cubed. Air is actually 1.16 kilograms per meter cubed. Very small. That's why that term will go to 0, because the density of the ball, the drag, is so much higher than that. Okay. Then we have minus mg equals m dv dt. Everyone understand why I switched A to dv dt? Because that's the fundamental equation, right? Okay. Now, again, if this was a missile, you'd have thrust on the left. If it was, yeah, that's good enough. Okay, cool. Questions? Does that make sense? So let's visualize, and I want to give you some other equations here. As this ball is picking up speed, This number increases, right? That makes sense? To the power of what? 2. What about this number? Say the same. So if this number on the left is increasing, this stays the same, what's going to happen? This is going to approach this. And what is this term will end up being? 0. When that happens, that is called terminal velocity. You see that now? You ever understood why terminal velocity occurs? It's because your drag force is equaling your weight force. And it can't pick up any more speed because it can't. Because that ball is pushing down. That's like it's grabbing the ball and pushing it, and it will only reach a certain speed. So if you set that to 0, your terminal velocity is 2 mg over rho CdA. Okay, so that's anytime you want to know terminal velocity, that's going to be your speed. But what I want to do is I want to plot from 0 to terminal velocity. So we need to use this fundamental equation up here, rho, or 1/2 rho v squared CD A minus mg equals m dv dt. Does that look like an equation that you could solve numerically now? You just did it, right? With h, okay? You could say, oh, you know what I want to do? Find m for a tennis ball. So I want you to try this. So find the mass, put it in kilograms of a tennis ball, not just tennis. It doesn't make sense, right? You can find the area, right? Because you're going to need diameter. So let's check a few of these off. Got the area. You could also find the density of a tennis ball, right? You can do that online, research that. We've got the mass, we've got gravity, mass. Start with a velocity that's really, really small. Otherwise, you can't kickstart the numerical method. Okay? If it's 0, it will never increase. Okay, so just give it some initial velocity first. What's left in this? Well, dv dt, that's what you're going to solve, which is delta v over delta t, right? So delta v is blah, 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 all that stuff times delta t, just like we did delta h, okay? This is where I want to have you try this now with a new set of equations to see if you can understand how we just coded it, okay? The last thing is your drag coefficient. And this is two equations. We just got to find it. Anybody know or remember Reynolds number equation? No. Oh, no, just the equation. There's, depending on how you do it, but this one I'm doing is 4 variables. Rho V D over mu. Yep. That is your density of the ball, right? Double check. It's been a while since I did this problem. I'm pretty sure it's the density of the ball. I have nomenclature in my code here. Oh, he didn't put it in. No, sorry. That should be of air. Yeah. That's for air. Yep. This is your ball velocity. Okay. Diameter of the ball. But this is your dynamic viscosity of air. You can find that. I think something to the -5. I can't remember. Actually, I'll probably give you those and you could check them. I have that. Yes. So mu you can use 1.8 e to the minus 5. The units are pascals. Why am I giving you this? Because the Reynolds number is less than 2 e to the plus 5. CD is 0.5, else CD is 0.2. So in this, what you have to do first in your for loop is calculate Reynolds number. Calculate your CD, which is an if else statement. Then find V of 2 or V of 3, and then time, and then it goes back up to the loop. Does that make sense? Anybody know ideal gas equation? Did you do that in fluids too? Remember what that is? P equals rho RT. Why don't you use this to find density of the air? Assume P is 101 kilopascals, and let's do 293 Kelvin, like my lovely units. Remember what R was for air? 287 joules per kilogram K. In your givens, you can put this equation. Solve for the density given those pressures. So let me just review this so you can get an idea of how to code this for homework 3. Okay, we have a tennis ball. We did a free body diagram, and we found that awesome differential equation, right? Which solves for terminal velocity or velocity of an object as a function of time. All right, we got drag, we got weight, we ignored everything else. Okay, there's no thrust, there's nothing in there, nothing spinning, none of the blah, blah, blah. Okay, we're going to solve this numerically with parameters of a tennis ball: the mass, the area, and the density of the tennis ball. Okay, start with this very, very small initial velocity. And we want to know, we also have the temperature and pressure of the atmosphere that we're doing it in. Okay. We can find the density of the air. We can use that density of the air and the Reynolds number to figure out what the drag coefficient is. It's going to start out this, which is laminar, and then it's going to go turbulent flow. Remember that? Okay. It should go from laminar to turbulent, I believe. Okay. It may not go, might be 0.5 for a while. So what you need to do is you need to put the givens in the givens in your for loop: Reynolds number, CD, delta V or V, time, and then that's your loop. And then plot V. So basically, I want you to plot V versus T. I believe it should do this, right? Increase and level off. And it should increase to the power of 2. That's what the curve is. So solve that numerically for me.